The historic Flushing Bridge serves as a centerpiece for the city of Flushing, Michigan. Directly connected to downtown Flushing, this 98-year-old concrete arch bridge is the only Flint River crossing in the city. The rehabilitation of the Flushing Bridge was a compromise solution that both increased the maximum capacity of the bridge and increased its stability. Today, the bridge serves nearly 20,000 vehicles daily. Pedestrians can enjoy this bridge thanks to the Flushing River View Trail that starts at the Flushing Bridge and meanders along the Flint River.
For our analysis of the bridge, we simplified it into a flat beam of supports. To remove more complexities in the math, we only analyzed a portion of the bridge between two of the supports. This allowed us to use methods we have used in class to find the shear force and bending moment of the bridge under worst-case scenario traffic flow. These equations can then be used to find the resulting normal and shear stresses the bridge must endure.
For analysis, we first found the distributed loads acted on the bridge. Our first load is from the weight of the bridge itself. To find that, we used the equation WB equals RHO, which was the density of concrete, times the cross-sectional area times gravity. We then solved for the distributed loads caused by traffic in the worst-case scenario for the bridge. We used 6 large pickup trucks to simulate the most weight the bridge will have to hold based on the traffic in that area. The equation used for that force is W2, which equals the number of trucks, times the mass of a single truck, times gravity, divided by length of the bridge section. We then added the forces together to get a W total for the bridge. When using our free body diagrams, our first step towards solving for shear force and bending moment was to find the force AY on the bridge. To solve for that, we used the equation W total divided by 2 times the length of the bridge section. Once we had the force AY, we could move to our free body diagram and solve for the shear force and bending moment. To solve for V, which represents shear force, we used the sum of forces in the y direction and found that V equals AY minus the W total times X. For the bending moment, we used the sum of moments around X, and we found that M equals AY times X minus the W total times X2 divided by 2. Once we had our equation for M and V, we plugged them into the equations for normal stress and shear stress. For normal stress, we use the equation sigma equals m times c divided by I. When solving for I, we cube the height due to the direction of the moment, and we also use the height divided by 2 for the c in order to solve for the stress at the bottom of the bridge. For shear stress, we use the simplified equation tau equals 3 divided by 2 times v divided by area. We are able to use a simplified equation due to the rectangular cross-section that the bridge has.
After finding the equations for the normal and shear stress, we graphed the functions using MATLAB. Both graphs matched the profiles we expected. The shear stress graph was symmetrical about the center of the span, had a negative linear slope, and peaked at the edges near the supports. The normal stress graph was also symmetrical about the center with a parabolic shape. It peaked at the center of the span furthest from either support.
For the concrete that was most likely used in our bridge, we found that its max normal stress was 50 MPa and its max shear stress was 5 MPa. Our max sigma at the center of the bridge span was 5.07 MPa and our max tau at the edge of the span was 0.34 MPa. To solve for the factor of safety, we took the max values and divided them by their accompanying calculated values. We then selected the smaller of the two numbers to use as the factor of safety for the entire bridge. After calculation, we found that the bridge was constructed with a factor of safety of 9.9.
During our project, we analyzed the Flushing River Bridge to find the shear and normal stress that it experiences on a daily basis. Through our research and evaluation, we made various simplifications to the bridge and the forces. While our values may not represent reality perfectly due to those simplifications, we were still able to gain an understanding of what happens to the bridge. This project allowed us to use our knowledge of materials and see the applications of what we've learned in class this term.